Let's talk about vertical asymptotes. If this is your first time of seeing my video, consider subscribing, follow my page, like and share this video to your friends. We have these functions here and we want to obtain the vertical asymptotes of these functions. Now, whenever we are asked to obtain the vertical asymptote of any function, there are three things we need to have in mind. First, we need to check if the function we have is actually factorizable. Secondly, we need to cancel out common factors both on the numerator and in the denominator. Now, after that, we need to set the denominator equal to 0. But let's take a look at this first function we have. We have f of x to be equal to 1 over x minus 3. Now, we have seen that we cannot actually factorize anything from both numerator and denominator in this function. And since we cannot factorize anything, we don't have any common factors to cancel out. So we need to set the denominator, which is x minus 3, equal to 0 in order to obtain the vertical asymptote of this function. So we have x minus 3 to be equal to 0. And then if we add 3 to both sides, we have x to be equal to positive 3, right? So this is the vertical asymptote of this function f of x. We have vertical asymptote to be equal to 3. Now in this case, we have y squared to be equal to x over x minus 1. And we know that this expression here, this function here, we need to simplify this function in order to obtain the vertical asymptote. Because we have y raised to the power of 2, we have y squared. So we need to make y the subject of the formula in this case. So the best approach we can take from the knowledge of indices, we have that we are going to multiply both sides by the power of half. So we have y squared be equal to x over x minus 1, all multiplied by the index of half. And then we are going to also multiply this by half so that 2 cancels 2, right? We are left with y equal to x all over x minus 1, all raised to the power of 1 over 2. Now let y be equal to f of x. And we also know from the knowledge of our indices that whenever we have anything raised to the power of half, it's as good as writing the square root of that thing. So f of x will be equal to plus or minus the root of x all over x minus 1. Now, we are going to separate this numerator and the denominator since the square root is covering both numerator and denominator. So we can rewrite this to be equal to plus or minus root x divided by root x minus 1. And from here, we have seen that there is no common factor to cancel out, right? So we equate everything under this root in the denominator equal to 0 to obtain the vertical asymptote of this function. So we have x minus 1 to be equal to 0. And then if you add 1 to both sides, you have x to be equal to 1. So the vertical asymptote of this function will be positive 1. Right, so this is the vertical asymptote of this function, y squared will be equal to x over x minus 1. And then we move to the next function we have on our list. We have x squared plus 1 divided by x squared minus 1. Now, if you take a good look at this function, you will see that the numerator is not actually factorizable. because we have x squared plus 1. It's more like sum of squares. So we cannot actually factorize what we have on the numerator. Unlike what we have on the denominator, we can actually use difference of two squares, right? But then it's not the case in the numerator. So since we have seen that we cannot actually factorize anything here, and so we cannot cancel anything here, we have to equate our denominator equal to 0 to obtain the vertical asymptote of this function. So we have x squared minus 1 to be equal to 0. And then add 1 to both sides, we have x squared be equal to 1. So if we make x the subject of the formula, we're going to take the root of 1. So we'll have x to be equal to plus or minus the root of 1, right? So what this means basically, the root of 1 is 1. What this means basically is that the vertical asymptote could be positive 1 or it could be negative 1. So vertical asymptote of this function could either be plus 1 or negative 1. So either of this case. Now to the last function that we'll have on our list, we have that f of x is equal to 4 over x squared plus 1. Good. So we have this function and we know that we cannot actually factorize x squared plus 1. So what we need to do, there's nothing to factor out here, and so there's nothing to cancel. So what we just need to do is to set the denominator equal to 0. So we have x squared plus 1 to be equal to 0. And then if we subtract 1 from both sides, we have x squared to be equal to negative 1. So if we make x stand alone, we are going to take the root of this negative number. So we'll have x to be equal to plus or minus the root of negative 1. Cool. If we look at this function, this expression here, we will see that this the root of negative 1 is actually out of real number system. So this is no longer, this is now a complex expression. It's no longer a real number. And so the vertical asymptote of this function is none. There is no vertical asymptote. What it means is that there is no, invisible line where this function is undefined. All right? So, it can actually happen. There are cases where you get to have no vertical asymptotes. So, I want you to have the conditions in mind. First, you need to check if what you have is actually factorizable. Secondly, you need to cancel out the common factors. And thirdly, you set the denominator equal to 0 to obtain your vertical asymptotes. In our next class, we will be taking vertical asymptotes where we have factorizable expressions both in the numerator and in the denominator. So I would like you to stay tuned and anticipate our next class where we'll be taking functions where you can actually factorize the numerator and the denominator, and we'll also be showing graphical representation of what this vertical asymptote actually are and what they what you can actually liken them to be in your graph. Right? So I hope you enjoy this class. I want you to share this video to your friends, like, comment, and subscribe to this channel. Hope to see you on our next class. Bye for now.